For our first problem, we're going to look at the volume per volume with percent solutions. How many mils of bleach do you need to make 200 mils of a 10% bleach solution? Well, whenever you see volume per volume, we're dealing with a liquid and a liquid. So 1% volume per volume means that there is 1 mil for every 100 mils. So if we have a 10% bleach solution, it would mean that you would need to add 10 mils of bleach to 90 mils of water. And that would give you a 10% bleach solution. We don't have 100 mils, we have 200 mils, so we would need to double that. So in this case, we would have 20 mils of bleach plus 180 mils of water to give us a 10% solution of bleach. Our next problem is a weight per volume problem. So with this one, we have something dry that we have weighed and something that is a liquid that we have measured. What you always need to know with a percent solution is that 1% equals 1 gram for every 100 mils that you have. So let's look at this problem. How much sodium chloride is needed to prepare 100 mils of a 25% weight per volume solution? Well, using what we have above, if 1% is 1 gram for every 100 mils, we have 25 grams for every 100 mils. So this one is fairly straightforward. Since the problem says we do have 100 mils, that would mean that we would need to weigh out 25 grams of sodium chloride in order to answer the question. For this type of problem, we are going to figure out how to prepare 500 mils of a 2% glucose standard from a stock 25% glucose standard. We need to know how much of that stock standard we would need to prepare that. So for this, you need to use the C1V1 equals C2V2 equation. With the C1V1 equals C2V2, I like to figure it out as the first side is what you have on hand, and the second side is what you need. So let's go ahead and fill these in. We know that on our shelf we have a 25% glucose standard. So now we know what we have. The concentration, or C, is 25. On the other side, what we need is 500 mils of a 2%. So on this side, the concentration is 2, and the volume is 500. What we don't know is what we'll put as X here, or V1. In order to figure out how much of that we need, we're going to have to do some math here. So on this side, we have 25X equals 1,000. If you divide both sides by 25, you get 40. X equals 40 mils. But we're not done there. So we have 40 mils. 40 mils of what? In this case, what we would have to do is take 40 mils of our 25% glucose standard and fill the container up to 500 mils of water, which would essentially be 460 mils of water. For this part of the presentation, we are going to review how to calculate standard deviation and coefficient of variation. There are quite a few steps here that you need to be familiar with. First one being, take all of the results that you have in your sample set and add them together. So in this case, we have 82, 85, 89, 85, 91, 90, 81, 85, 93, and 89. The first thing you're going to do is add up all of the numbers within your sample. Here, the summation, which this little letter E stands for, equals 870. The population in this sample, N, equals 10. In order to find the mean, we take the summation of all of those added together, divided by the number in the population, which is 10, and that gives us an average of 87. Our next column is where we take the mean minus x. So we have our mean down here, which is 87. We are going to subtract that from all of our results above. So in this case, you would get a 5, 2, 2, 2, 4, 3, 6, 2, 6, and 2 by subtracting the mean minus the x. Now, the third column, you take everything from the second column and you square it. 5 squared is 25, 2 squared is 4, 2 squared is 4. You can see where I'm going with this. When you get to the end, you do need to figure out the summation of the mean minus x squared, and that gives you 142. The next step is to use the standard deviation equation, where standard deviation equals the square root of the summation of the mean minus x squared over n minus 1. From the previous page, when we added up the whole column of the mean minus x squared, we got 142. And the first column, we saw that the population was 10. There was 10 samples there, which is what our little n stands for. So n minus 1 equals 9. So we get that from the 10 minus 1. If we take 142 divided by 9 and take the square root of that, we get a standard deviation of 4. So just a little bit of review here in how to plug the standard deviation into a Levey-Jennings chart. I've created a chart here for you. We know from the previous page that our mean is 87. For every standard deviation that we have, we increase the standard deviation by 4. So 87 plus 4 is 91, 91 plus 4 is 95, 95 plus 4 is 99. So we've got 1 standard deviation, 2 standard deviations, 3 standard deviations. Going the other direction, we have the mean in the middle, which was 87 again. Now going backwards, 87 minus 4 is 83, which is minus 1 standard deviation. 83 minus 4 is 79, which is minus 2 standard deviations. And 79 minus 4 is 75, minus 3 standard deviations. Usually across the bottom of the QC chart then, we have the different days that the QC may have been run in the lab. So we want to make sure that as we run our QC on these various days, that we try and stay between plus or minus 2 standard deviations. So ideally, you want to stay in between these ranges here. So that's why we do have Westergaard rules to help us figure out if we are staying within our means here. So if we run our QC on day 1, and the tech runs, let's say this is a glucose, gets a glucose of 87. We'll put that right on here. Day 1 got an 87, he's jumping for joy. You should stay right on the mean, that's a great place to be. Day 2, the tech comes in, runs the glucose again, and he gets a 91% on the QC vial. Well, still within 2 standard deviations. Okay, hasn't gone out to where he should be, still looking pretty good. Day 3, tech comes in and gets an 83. As you can see, we are still within our confidence interval here. We like to stay between plus or minus 2 standard deviations. So day 4, tech comes in, gets another 91 here, and then all of a sudden, day 5 comes in, gets a 96. So as you can see, this 96 has gone just a little bit above where we want to be. This is called a 1-2S warning with the Westergaard rules. This is the only Westergaard rule that would be a warning. If you do have a warning, you take note of it and you can continue on doing your QC. So 12S equals a warning. So the tech comes in, does some, he did some calibrations and things like that. The next day comes in, it's down to a 91. So everybody's happy. Well, let's say then the next day comes in, gets a 96 again, still a warning. Okay, we're at 12S. He's over 2 standard deviations 1 time. Now, let's say they try to run QC again. They get a 96 again. Then we are looking at a 22S, which is a rejection. So once that QC has gone out 2 times over 2 standard deviations, then we're looking at a rejection. Now there are other Westergaard rules that you need to be familiar with. This is just a review of 12S being a warning. Out the first time it's a warning, the second time it would be a rejection. Other things to make note of on the QC chart here is the difference between a trend and a shift. So if we had QC that started off down here by the 79, and the next day it was up to an 80, 81, 82, and we start coming up like this, this is known as a trend. This can happen over time from having reagent degradation, or things, or reagent getting older, QC material getting old are usually the typical things that can happen. Another thing that can happen is having QC be nice and happy, then all of a sudden it jumps up. So we're down here, and then all of a sudden we get a big old jump like this. This is called, one big jump is called a shift. Things that can happen are all of a sudden some type of instrument malfunction. Let's say there's a bubble in some of your reagent lines or something like that, or in your reagent probes that could cause a sudden shift in your quality control. One more thing to make mention of on here is coefficient of variation. What is the coefficient of variation? The coefficient of variation shows your spread in your numbers. How far apart are your numbers? So going back to our first page, you can see here that our lowest number on here, let's see, would be about an 81, and our highest number looks like it would be a 93. So our spread goes from 81, whoops, I circled the wrong one, 81 to 93. Okay, so that's a pretty big spread, but you want your coefficient of variation to stay less than 10%. Let's see where we are with this one. In order to calculate the coefficient of variation, you need to take your standard deviation, which is what we found down here, that was 4, divided by your mean, which we know was 87 from the following page, times 100. So we take 4 divided by 87 times 100. Our coefficient of variation is 4.6%. That is good because we like to keep it less than 10%.